Ladies and gentlemen, Mr. Chairman, thank you for the invitation and for giving me the slot to present our latest work at MSI that is trying to give some new content on the sound field of a direct field acoustic test. Let's try to put this in context. Our work is very much focused on a specific acoustic test that happens in the space industry. This is a qualification test necessary to make sure that a launch there is no major issue or damage to a structure. So what happened before launch? There's an extensive test campaign which includes an acoustic test that replicates the launch noise. So there are different type of tests: vibration, static, acoustic, shock. So there's different, and spacecraft are mandate to spacecraft manufacturer mandate by the launch authority to run these tests. For what concerns the acoustic test requirements, there are so there is a legacy developed over the past 40 years of activities, 50 years, in which tests were conducted in specific chambers, Reverberant chambers. These were purposely built, and for the reason, especially the European launcher manual, so the Vega, the Soyuz, the ARIANE V, they specify that the acoustic field has to be diffuse. This is not the case in other launchers. So the Americans or Falcon, SpaceX, the ULA, so Delta, Japanese, so they don't specify explicitly the need of diffusiveness, or the field has to be diffused. And the reason is that it is intended, it is assumed that the test happens in a reverb chamber, and therefore the field has specific characteristics. In practice, these tests happen using a spectrum as a reference. The launcher manual specify the level, the sound pressure level at each octoband or third octoband, depending on the launcher. And what happened in the chamber, the operator uses a manual control, or like an equalizer, like a real, if you think of your hi-fi equalizer, or an automatic control system that makes sure that the sound pressure level measured in different points matches the one that has been assigned. There are, as I said, there is the Reverberant chamber that has been used over the past 40 years. You can see an example here in the picture. These are thick walls, large chambers. They are large chambers are the order of 10 by 10 by 10. Can you imagine? So like 1,000 cubic meter is a relatively large chamber. But lately, relatively lately, because it's 20 years that these tests have been going on, direct field acoustic testing has become a valid alternative. There have been many projects. In the States, we have qualified over 100 satellites to acoustic using direct field acoustic test. And so this is now a rather new test for many, especially in Europe. And so there is still some questions open, and there is still some answers to be given. But when we answer and we're trying to address these, we need to remember that there are two reasons why there is the test is done. One is the acoustic, so to replicate or to simulate the frequency loading that happens in the fairing, and second is to measure the vibration response of whatever is being tested. So there are two camps. There's a structural camp and an acoustic camp, and many times the requirements are not exactly the same. So what the structurist wants is that the structure vibrates at the level that are expected, and the acoustician would like to have a perfectly diffuse and uniform field. So what we are talking here is to run a test using loudspeakers. These are not commercial loudspeakers. We could do with commercial loudspeakers, but these are not commercial loudspeakers. These are purposely built loudspeakers to trying to get an acoustic field which is as close as possible to what the industry knows, which is the reverberant chamber. Just for information, the newly made, so the latest addition to the ARIANE family, which is the ARIANE 6 launcher, is the first one that is not flown yet. It is the first one that acknowledges DFAT as a possible test means, but there's still some details missing on how to quantify and qualify a satellite with DFAT. So the question is, are all the DFAT, so in the reverb chamber, as long as the size are the same, so you have these big chambers, and as long as the design, the shape is the same, then there is no much difference between the field produced in one or another. Is not a major difference, and therefore satellite manufacturer, they can go to a chamber A or chamber B. In Europe there are 3 or 4. There will be few questions asked. Mostly they will accept the result without too many questions. And how about DFAT? So all the direct field acoustic tests produce the same result. Can we apply this same metric to all of them? Or how could we even compare the two? So what are if the accelerations are the same, is that enough to say, or equally or relatively similar? Is this enough to say that the two fields of a reverberant chamber and a direct field are the same? So these were the questions that brought us to work along this way, and we are introducing and we're discussing with you this new function. Could be a metric, is a single indicator function, the SIF. So let me get from the beginning where we started with this. This was a study published by Grace Gardner, that was at JPL at the time, now it's at DSI, back in 2000. So this is a 22 years old paper, and he looked at the pressure from microphones in the fading, and he created a correlation between this microphone to derive a coherence function. So the coherence is how these 2 points are correlated, and he looked at from a vibroacoustic numerical simulation point of view to what the theoretical field would look like, a theoretical reverberant and diffuse field that approximates to a sinc square function. So he said, okay, this is what the sinc square function is. That's what I get in the fading. So actually there is a difference. So the field in the fading, the acoustic field, is not as diffuse and reverberant as we tested to. Now there is a debate in the industry on whether or not we should use this assumption of diffusivity and reverberation, but this is not the topic now. So by looking at these 2 curves, I thought, well, probably by making a difference we could get somewhere. And so when it comes to diffuse field is a very is a very encompassing word. It's a very large spectrum word. So there are definitions, there are different takes. We can take that there is a diffusiveness, there's a diffuse field in the acoustic, in the audio engineering sense. So here we can take it according to the international standard as the sound field, which in a given region is statistical uniform energy density, which means that waves come from all over, from infinite direction. If one goes to the max, and look at the coherence, or look at 2 points, how these 2 points are correlated, it boils down to a sinc square function. So sine over kr, where k is the wave number and r is the distance between these 2 points. So we're assuming with all the assumptions related to this field that the coherence square can be represented by the sinc square function. On the other hand, when we do a test and we have a number of microphones, we do measure the coherence as a ratio between cross power and auto power between these two points. So we have here two functions, a measured function and an expected or theoretical value that would, in principle, be the same if the fields were exactly the same. So in theory, we have the curves that are black on the screen, so there's a black screen or blue on one side, and in practice we have the green or blue curve that are measured in large reverb chamber. These are two different chambers, and so we can see that there is the chamber do approximate the field, the theoretical field, pretty closely. So there is a resemblance in the curves, in the shape of the coherence square function. So if we use the difference at each frequency line, we could come up with a function, so a function of frequency, which subtracts the two from one. So the idea is to have a one as an ideal sound field, acoustic sound, ideally diffuse sound field. So in order to have a field, if this metric or this function could be worth looking at, we have designed an experiment, and we had data from a reverberant chamber to see what would look like. So one, a sync indicator function calculated on reverb chamber, and the other one calculated on a setup where all the speakers, so there is a number of speakers, number of microphones, all the speakers are driven by one same signal. So the field is very coherent. So there's one signal going through all the speakers, and this signal is then being picked up by all the microphones. And it is clear that the gray curve shows that the coherence function is very, so this sync indicator function is very small, so it tends to 0. Whilst on the other hand, the reverb chambers tends to 1. It is also possible to see that in the lower frequency, the reverberant chambers do show a dip in these difference, and this is known. This is easily explainable by the fact that reverb chamber have a minimum frequency below which the model density is too low to create a diffuse field and a reverberant field. So there's always depending on the size. This is large frequency. This is a large chamber, so the frequency is pretty low. But the smaller the chambers, the higher that the frequency becomes. So the wider that the discrepancies, the region of which there is much difference, more difference between a theoretical and a measured field is visible. The other question that we asked was, okay, let's try to, what would be a theoretical field? So the theoretical field would be in simulation. So these are simulated. So these are 24 microphones, so 23 pairs of points in which the field is numerical. So it's like one of those vibroacoustic simulation packages, which assume an ideal correlation function between two, so the sync function. And so if you measure these, then we have a test of in an ideal reverb chamber, and in fact the SIF, so the sync reverb becomes 1 because the difference is very it becomes then 1. That's what would be theoretically expected. Now, when it comes to look at the data, acoustic data for spacecraft application, we have, as I said, three plots that we would be then looking at. One is of course, the spectrum that is being given. As I said earlier, that is a requirement from space, from the launcher. So you have a spectrum to meet. So there is a number of microphones, and the average of microphones should be pretty much on top of this curve, and definitely within tolerances. Then there is a uniformity, as the ARIANE 6 demands, so that every microphone should be no more than 3 dB difference from the average. And then there is this newly defined SIF. So these three plots should give enough details, enough evidence to a test engineer that the field that's exciting the structure is close to what has been used for the past 50 years, which is the reverberant field. This is the same type of plot, but for a MISO multi-input single output. So that's the case where all the speakers were driven with one single signal. And so even if the average of all the microphone is on top of the target, the coherence is very low. So it's very, so the gain is not very low, but it's very high. So it's very different from, so the SIF is very low. It's very different from what I theoretically expected. And also the uniformity is obviously not meeting the requirement. So there are lines a bit, which many points there is I would say an 11 dB difference between 2 points. So a field in which there's 11 dB difference between the points is actually not what we require. It's very non-uniform field. This is one of the tests done with DFAT. So we use 24 control microphone, and we drive 8 stacks of speakers. So there is 8 different signals, independent signals going to the speakers, and we achieve what is a test which is very close to a reverb chamber. You can see the 24 microphone very closely matching the reference, and none of them going more than 2 dB from the average. So it is actually a test which resembles very close to the reverb chamber. There is a lot of things we can do in a DFAT. So the answer to, are all DFAT the same? No, all DFAT tests can be, every DFAT is different, and SIF, so the sync indicator function, is one parameter that can be calculated and will show a difference between different fields. Uniformity is another parameter. Of course, a uniform field will entail or will imply that the waves are coming from many directions. So you would also have the other condition for diffusivity. So there are still questions and debates on whether or not the launch has a field which is reverberant or not. But in practice, we are now striving to recreate what a reverb chamber does, and I think modern technology allows us to plot to achieve that field and to actually compare it to a reverb chamber, and the comparison is pretty impressive. Now there are still some points on the SIF. So the SIF is dependent on the calculation of the coherence function from time data, which means that there is a sampling frequency bias effect. So depending on the sampling frequency, the curve can be more or less hairy, and therefore we might get different overall value over the frequency range. So when it comes to looking at the SIF and using it as a metric, one is to be aware that there is a signal processing to be applied, and has to be consistent. So this metric can be used as a comparison, a relative comparison function, provided that all the processing has been done from time data exactly the same way. So it becomes a meaningful way of looking at the property of acoustic field. This is not again. This is an initial concept and seem to be very valid. We are still trying to create more cases, more or less controlled, so we can apply and generalize the concept. Thank you. I am happy to provide any answers to questions that the audience and the chairman may have, and I will remain available to any further, my emails and contact number there for any further